So here we have three balloons, one filled with air, one filled with refrigerant gas like you'd find in your air conditioner or refrigerator at home, and one filled with helium gas. We begin by taking the air-filled balloon and dunking it into the liquid nitrogen. We wait for a little while for the liquid nitrogen to cool the air inside of the balloon down. When we take the balloon back out of the liquid nitrogen, we see that it has completely collapsed. This is because the balloon is filled with both nitrogen and oxygen. At the temperature of liquid nitrogen, oxygen fully liquefies. So what we actually have inside of the balloon when we take it back out is liquid oxygen as well as liquid nitrogen. Because the volume of a liquid is far less than that of the same material in its gas phase, the balloon shrinks down because of this change in volume. Now we take a look at the balloon that was filled with helium. Unlike oxygen and nitrogen that you find in the air most commonly, helium has a liquefaction temperature far below that of liquid nitrogen. Because of this, when we put the balloon inside of the liquid nitrogen, we see that the balloon does not actually completely collapse. It simply shrinks down a bit. And this is because inside of the balloon, the helium is still a gas. Now when we take it back out, we see that as the balloon warms up, the gas expands back to its original volume, and the balloon reinflates. Now we look at the balloon that was filled with a refrigerant gas. This refrigerant gas, unlike the other gases we've looked at so far, has a liquefaction point, and in fact even a freezing point, way above that of liquid nitrogen. This means when we place the balloon inside of the liquid nitrogen, we see that it has completely collapsed. And this is because the refrigerant inside of the balloon has fully solidified. And we actually see that when we take this balloon back out, it does not re-expand right away. That's because we've cooled the refrigerant so far below its freezing point, we have to wait for the temperature to rise back up to nearly room temperature before the balloon will reinflate. So we can wait several minutes and we'll see that the balloon will still be completely frozen. This is similar to like if you had an ice cube out, an ice cube does not instantly melt when you take it out of the freezer. So here we have a glove like you'd find at a doctor's office or maybe a dentist's office. You see it's very stretchy and very rubbery. It's made out of some nitrile rubber. Now what happens if we take this glove, we put it into liquid nitrogen. Here we take the glove, we dunk it into a dewar of liquid nitrogen, and we wait for a little while for the liquid nitrogen to cool the glove down. So the liquid nitrogen is very cold, it's at minus 320 degrees Fahrenheit, so it takes a few seconds for the glove to cool down to this temperature. We then take the glove back out, and we see that now the glove is very rigid. And we see, in fact, that it's so rigid and so brittle that if we take a hammer and hit the glove will actually completely shatter. Here we look at what happens when we take an LED, or light emitting diode, and place it into liquid nitrogen. We start with an orange laser diode, and we put it into the liquid nitrogen. We see that the laser diode changes in color, from orange to yellow and then to green. Now, when we take the laser diode back out from the liquid nitrogen, and we wait for a little while, we see that the color then changes back in the opposite direction, from green back to yellow, and then finally back to orange. This takes a little bit longer because it takes longer for the diode to heat back up than it did to cool it down in the liquid nitrogen. So now let's look at why this color change happens. When you take an LED and you connect it to a battery, current flows through the LED and the LED emits light. Now if we zoom in to the actual LED at a microscopic scale, we see that an LED consists of two levels, one where there's electrons and one where there are no electrons. So now when we connect it to a battery, the electrons flow and they go towards where the electrons would like to go. In doing so, and when they jump down from this upper level to this lower one, they emit light. Now the color of the light that's emitted by the LED is dependent on the spacing between this upper level and this lower level. When the spacing is small, or the gap is small, the light emitted is at lower energy. This means the light is shifted towards the red or the orange. When the gap is larger, the light emitted will have a higher energy, and thus the light will be shifted towards the green. Now what happens when we cool down the LED? When we cool down the LED, we also cool down all of the electrons within the LED. Because the electrons are colder, this gap actually increases. Because this gap increases, the color of the LED will shift towards the blue as we cool it down.
What you're looking at is a phenomenon sometimes referred to as quantum levitation. In this video, a material called a superconductor is floating on top of the magnetic field produced by a set of square magnets. Perhaps you've tried something similar yourself with ordinary magnets before, but you probably found that after just a split second, the magnets would snap together instead of remaining in place. What's even more remarkable about this situation is that it's not just levitation. The superconducting material is essentially locked in place. I can turn the magnets over, and the superconductor follows right along. We've already seen that material properties can change dramatically when they're cooled down. When some special materials are cooled below a certain so-called critical temperature, their electrical resistance completely disappears. It doesn't just get very small, it drops to zero. This has been known for well over 100 years, and was first discovered in the element mercury after cooling it down to around 4 Kelvin. Achieving such a low temperature is quite hard. For the past 100 years, physicists have been searching for materials that can superconduct at much higher temperatures. The superconductor that you've been looking at has a critical temperature around 100 Kelvin, which is luckily a little bit above the temperature of liquid nitrogen. So all of the experiments that you see in this video start with the superconductor sitting in boiling liquid nitrogen, like you see here. In addition to having zero electrical resistance, another characteristic property of superconductors is that they can totally expel magnetic fields from their interior. You may know that magnetic fields are generated by circulating currents. So, a way to expel magnetic fields is for the superconductor to set up within itself just the right set of circulating currents to undo the effects of any magnetic fields that try to pass through the superconductor. The same sort of thing happens in regular conductors, but because in a superconductor there's no electrical resistance, these internal currents can continue without any loss. The superconductor can therefore completely expel magnetic fields. After the superconductors have been sitting in the liquid nitrogen and cooled down below their critical temperature, we can take them out and place them over a magnet. Remarkably, the superconductor interacts with the magnet in such a way that it remains locked in place. We can reposition it, change its angle or its height, and the superconductor will levitate stably above the magnetic field. If instead of square magnets, we use a set of round magnets, the magnetic field produced now has circular symmetry. So, if we move the superconductor to this magnetic field, the superconductor is now free to rotate about the axis of the magnets. It remains locked in place, except for the rotational motion. What we've seen so far might explain why the superconductor can levitate above a magnet, but how can we understand why it will float below when the magnet turns upside down? To understand this, we also need to know that higher temperature superconductors, like the one we're looking at, actually allow a little bit of magnetic field to leak through their bodies. However, this magnetic field penetration can only come in discrete bits of field leakage, whose little vortices of current surround so-called flux lines that go through the superconductor. These flux lines can actually repel each other and form pretty ordered arrangements. Even more, these flux lines can get pinned in place due to imperfections in the superconductor material. When the flux lines get pinned, the magnetic fields don't like to move around, and this causes the superconductor to get locked in place above the magnet. Locked relative to the magnetic field, even when it gets turned upside down. But there are other fun things we can do with the superconductor. For example, we can take it out of the liquid nitrogen and place it on top of a large circular track on which it levitates. If we give it a little kick, it'll circulate until it warms up above the critical temperature. If we take two superconductors and place them on the same circular magnetic track, we can see that they can pass over one another without interacting. This is because they don't generate their own magnetic fields, they simply expel the magnetic field that they are placed in. Here you see a close-up, where one superconductor passes over the other without interacting. And again, because the magnetic field lines are expelled regardless of whether the superconductor is above or below the magnetic track, this circulation can occur even when the superconductor is hanging below the magnets. Over time, the superconductor slowly warms up, and eventually, its temperature is above the superconducting critical temperature. At that point, the superconductivity wears off, and the superconductor falls down to the magnet that it had been levitating on top of. At that point, we need to put the superconductor back into liquid nitrogen to cool it down below its critical temperature before we can play with it again. Luckily, that gives us time to think, because there's a lot we still don't know about superconductors. For example, physicists still struggle to describe exactly how high-temperature superconductors work. And because we don't have a full theory of their properties, it's difficult to predict or to make superconductors that work near room temperature. But maybe in the future, one of the students attending the Cambridge Science Festival will think up some new ideas and push us towards a more complete understanding.